Good morning, everyone. Hope you guys are doing well. Sorry that I am gone today. I'm at a conference in Oconomowoc, but I will be back later today if you do need anything. Tests are graded, grades are in. If you would like to see your test, you are welcome to stop by anytime before school or after school, or if you have A2 or B3, you can stop by, or we'll get them back next class. Hopefully you've gotten a blue book by now. You can see that this book is a little larger. This unit will take us all the way up until winter break. So there are a lot of different areas to look at in here. And so we'll start with today's lesson. Today's lesson's a little bit interesting in that it is really good, but it also has a few things that aren't super needed, which is why I wanted to create a video instead of just having you guys just go through and do some things you didn't need to do. So there are some really good things in it, and so we'll get kind of going from there. So we're reviewing the past. You guys did a lesson in past years that dealt with Scott and his push-ups. If I read here, it says, Scott's going to a gym to get in shape. He began by doing push-ups. On the first day, he could do 3, and then he found he could do 2 more push-ups each day. He kept track of the number of push-ups doing this diagram. So you can see he did 3, then he did 5, then he did 7, then he did 9 on each day. And so it says make a table and write an explicit and recursive equation for f of n each day. So if I make a table, I'm just going to have a basic table here with days and the number of push-ups. So on day 1, he could do 3. Day 2, he could do 5. Day 3, he could do 7. And so on and so forth. I could do 4 and 9 here too. Something to note then. So the explicit equation is much more important to math as we continue to get more and more complicated. So the explicit equation here, if I think about this, I know that the function of n, or like we could write this as y equals, we could write this as f of x equals, but they did f of n, where n is the number of days. I can see here that we're going up by 2 each day. And since we're going up by 2 each day, and since this first difference is constant, I can call this a linear equation. And so therefore it's 2n. Now I do have a y-intercept here, and if I think of going back to day 0, that y-intercept is 1. And so there's my explicit equation. And we have something that just kind of is, I would say, what we're used to seeing, especially lately. This is how we could get a quadratic equation. We've had a lot of explicit equations so far. We also, thinking back to Math 1, we had what we call a recursive. And a recursive is important. There are some values to it, but it also isn't like something that we use a ton. And so it's not a bad thing to learn. It's not a bad thing to use, but like a lot of times we just don't, I would say, have a ton with it. And so the recursive would be this, where we define the first term. We say that like f of 1, the function when the day is 1 is 3. And then we say f of n is equal to that previous term, f of n minus 1, and then we're just adding 2 more each time. This isn't really overly helpful when you start getting more and more complicated equations, but it is interesting to note here that you can see we're just adding on a constant here. And so something to note is, okay, if the rate of change is constant, if that first difference is constant, it's linear, and then you have a constant rate of change being added on there. Okay, so they obviously are going to get us a little bit different of a question here. And so this is a big promotion at the gym last year required Scott to keep track of the total number of push-ups he had done in March. The March Motivation promotion raised money for charity by finding sponsors to donate based on the number of push-ups completed. Scott used the diagram and table below to show the number of push-ups he did each day and the total number of push-ups he did in the month. He completed 3 push-ups on day 1, so same thing. He's still completing 3 on day 1. But now what he's doing is on day 2, he's going to do 8 push-ups. He's doing that because he did 3 for his day 1, and then he's going to do 5 more or 2 more than he did on the previous day in addition to the original 3. So you can see here this g of n function, his table, well, he's got all of these things going on here now. Well, the question they ask is, write the recursive and explicit equations for g of n. This is not something that we are going to focus a ton of time on today because this isn't going to be something that's going to come up in this unit. What we are going to focus on is the accumulated number of push-ups given in the day. And so we're going to see, can we fill out this table and figure out some more things about this? And so here, I'm going to almost just skip number 1 for a second. We'll come back and talk a little bit, but that's not really where our focus is. Instead, our focus is this table. It says Scott was proud of the money he raised last year. This year, Scott decided to take March motivation to a whole new level. He plans to look at the push-ups he did last year and do that many push-ups each day. So, last year, this is the number of push-ups he was doing each day. 3 on the first day, 5 on the second day, 7 on the third day, 9 on the fourth day. And therefore, how many has he done in the month? Well, he did 3, then he did 8, because these two things add to 8. Here, he now did 15 total, because these 3 things add to 15, and so on and so forth. So this year, he's really going all out. He's going to take the total number of push-ups he did per month, and he's just going to do that many per day. And so as we look here, the total number he did per day, well, this would be 24. I'll keep going here. This was 11. You can see, therefore, we're going to add 11 more, so this would be 35. So this will be 35. Now, if he's doing this many per day, well, he did 3 the first day. Now we have 3 plus 8. This is going to be 11. Now it's 11 plus 15. This is going to be 26, 50, 85. As we're just adding here, then 3 plus 8 is 11. 3 plus 8 plus 15 is 26. 3 plus 8 plus 15 plus 26 is, or plus 24, I'm sorry, is 50. You can also just take the 50 and the 35 and add together to be 85. Okay, so we have this table. So we can answer one of his questions. Otis, you're fine. And so as we add, we can see here, how many push-ups will Scott do by day 4? He will complete 50 of them. And so you can just see kind of the summation of that number. Now, here's the kind of crazy part of this table and what's a little bit cool. We saw that this was 2n plus 1. When we wrote the explicit equation here, it was 2n plus 1. Okay, so that's what we did on that first thing. Now here, you can see, if we look, the first differences were 2, 2, 2, and 2. And therefore, this is a linear equation. Here, if I look at my differences, 5, 7, 9, 11. The first differences are not the same. However, the second differences are the same. You can see the second differences here are the same. And so because of that, I'm going to tell you, and again, this is not something we're going to have to come up with this chapter, but it's n squared plus 2n. And so, okay, so the first differences are the same. First differences are the same. It's linear. Now, I want to make this red if I can. Nope, I can't do that. So I'm going to have to erase. So the first differences are the same. It's linear. Here, the second differences are the same. It's quadratic. If we look at this new one, 8, 15, 24, 35, those differences aren't the same. 7, 9, 11, those differences aren't the same. 2, 2, the third differences are the same. This is going to be cubic, which is what we're going to deal with this chapter. So this whole kind of setup of a problem is just so we start understanding kind of what's going on here. Okay? Now, it says how many total push-ups will Scott do on day 4? We already answered that. On day 4, he's going to do 50. Write the recursive. We're not going to worry about that. without finding the explicit equation, make conjectures the type of function that would represent the explicit equation. This is really the biggest takeaway from this, is that as we look here, it's going to be an x to the third function. It's going to be what we would call a cubic function. So we're going to deal a lot with cubic functions this chapter. Okay, how does the rate of change compare? So this is, again, an important thing. In the first problem that was linear, our rate of change was constant. We were adding 2 each time. Now, if it's quadratic, our rate of change is actually going to be linear. If you go back up here, you can see this was the quadratic. Our rate of change is this first column, 5, 7, 9, 11. That's linear. Okay. Our third one is cubic. You may start being able to then, I would say, hypothesize, well, if it's cubic, then our rate of change is going to be quadratic. Okay? And so that's kind of really the biggest takeaways that you should have here, is that like the rate of change is always going to be 1 degree less, and we'll learn that term a little later, than what we have. So this is our takeaways. So the rate of change of a linear function is constant. The rate of change of a quadratic function is linear. The rate of change of a cubic function is quadratic. So it's just, this is x to the third, this is x squared, this is x to the first, and then these rates of changes are 1 less. The recursive equation is not something we're worried about. Now, in the explicit, I get most of you write y equals mx plus b here. This is totally fine. You may know the quadratic function. It is in standard form y equals ax squared plus bx plus c. There's some level where some people instead of m call that a, but it's just so commonly known as m. But you'll see why, because the cubic function is y equals ax to the third plus bx squared plus cx plus d. And so you can see it just keeps going and going, where it goes in standard form to the third, to the second, to the first, and then a term with no x. And so technically you could write these for as long as you wanted, for as many things as you wanted. Like to the 7th power would be y equals ax to the 7th plus bx to the 6th plus cx to the 5th, so on and so forth. So it becomes very formulaic. Okay? There's not a lot to take away from this lesson. It is important to take away that we are going to talk about x to the third. It is important to take away that the rate of change is cubic, that understanding the third differences are the same. And so those are the main things to take away. We have a retrieval here. It says place the appropriate inequality sign in the expressions to make them true. This will be important this chapter just to kind of think through some things. So if A is greater than B, so maybe that's 12, and maybe this is, oh, I can do this for Eli. If A is 7 and B is 6, so A is greater than B, then 1 over 7 is blank 1 over 6. And you could just type that in the calculator, but 1 over 6 is bigger. So this is kind of an interesting thing where if A is greater than B, then 1 over A is less than 1 over B. So kind of a cool thing you could just plug around a little bit. And then we will get to do long division this chapter. We will have a whole section on it, but we'll do a one here quick and just see if you can remember. 23, does it go into 7? No. 23, does it go into 71? And the answer is yes, it does 3 times. So we divide, then we multiply 3 times 23, we get 69. We subtract, we get 2. We bring down the 4. Does 23 go into 24? Yep, once. We take 1 times 23. We subtract. We bring down the 9. Does 23 go into 19? No. We multiply, that's just 0. So then we get to bring down again. Does 23 go into 196? And the answer is yes. And it may be a calculator thing for some of you, but it goes in 8 times. 8 times 23 is 424, 184. And so then we get a 12 left over. For those of you guys who forgot, that's called the remainder. This is 3108, remainder 12. We'll talk more about this in lesson 5. But is it a factor? And the answer is no, because there's a remainder. Okay. You'll have the ready, set, go for homework. It should be, the ready and the go are both really good. The set is okay. It's fine. It's all good stuff. There's I would say plenty of time to figure things out and work through it. As you are doing the ready, you should be able to do them all. That should be totally fine. The set, I would say everything should make pretty close sense. Maybe the rate of change in 12 is a little beyond us, but that's okay. I'm not really overly worried about that. You definitely should be able to maybe get close to it. And then for your homework on 13 through 16, you do not need to write the recursive rule, but you should be able to do everything else. And then the go is good. It should make total sense. So let me know if you have questions. Hope you guys have a good day, and we'll talk to you later.